In this work, we aim to build robots that can help humans do different tasks at home. We want these robots to be socially intelligent, which means that they should be able to infer what the humans are trying to do by observing their actions, and coordinate with them in achieving these goals effectively. To do this, we hypothesize that robots must conduct probabilistic assistance. Here is an example. When a human walks to the kitchen, the robot will predict all the goals that are consistent with this action, and it will try to help according to all these goals, in this case by walking to the kitchen. The human then grabs 2 forks, and the robot restricts the set of possible goals, and it helps the human by handing them 2 plates. Finally, when the human puts the 2 forks on the dining table, the robot can infer what the goal of the activity is, and it will help by putting the 2 plates remaining on the dining table. To build robots with such a capacity, we propose a new embodied assistant approach, or NOPA. For more details, please refer to the main paper. To evaluate our method, along with different assistant approaches in a scalable and reproducible manner, we introduce a new embodied assistant challenge, Online Watch and Help. Here we will have a home apartment and a main agent that will be playing the role of a human and will have to do different tasks, for instance set up a table. Meanwhile, a helper agent will have to infer what the task the human is trying to do and help them in performing this task as quickly as possible. We use an open-source multi-agent virtual household platform, Virtual Home Social, to simulate a wide range of real-life household tasks in realistic virtual apartments. We show here a typical example of how our approach successfully conducts online goal inference in this challenge. In the upper right panel, we show the predicates and their counts proposed by the approach as possible goals. For instance, on apple coffee table means putting 1 apple to the coffee table. We also show the probability of each predicate count pair produced by the approach at each time step. In this example, the main agent wants to set up a table for 3 people. When the agent walks to the dishwasher, our approach eliminates predicates that are inconsistent, in this case objects that are not in the dishwasher. As the agent walks to the kitchen table, the approach eliminates the predicates that have to do with the coffee table, and increases the predicates that are consistent with the actions. And so as the agent takes actions, the predicates will be updated, and the helper will be doing the best action to help. Our approach also exhibits interesting emergent behaviors. Notice here how the helper agent hands an object to the main agent so that they complete the task. Or here, where the helper corrects its behavior, in this case, putting the fork back into the cabinet once it sees that the main agent is doing the task alone.